Every dot you see here is data. Every line, surface, and direction hiding behind it is mathematics. Machine learning isn't magic. It's geometry, it's vectors, it's spaces you can't see, but models learn to navigate. Welcome to this channel where we break down core machine learning from first principle to real intuition. No buzzwords, no black boxes, just clean math, clear visuals, and why things actually work. In this video, we start at the foundation vector spaces, RN, and geometry that powers ML models. If you ever train a model without fully seeing what it's doing, you are exactly where you should be. Let's build the intuition. Now, let's talk about why machine learning is geometry, not just a code. When you train a model, you are not just running an algorithm, you are placing points in space. Each data sample, that's a point. Each feature, that's a dimension. And your model, it's simply trying to find the best geometric structure, a line, a plane, or a surface that explains how these points relate to each other. Even something as simple as linear regression is just asking one question: which direction in space best fits this data? Once you see machine learning this way, concepts like loss functions, gradients, and optimization stop feeling abstract and start feeling usual. Now, the mathematics of machine learning rests on three fundamental pillars. First, linear algebra. This is how data is represented and transformed. Every data becomes vectors, and every model learns directions, projections, and geometric structures in high dimensional space. Second, calculus. This is how models learn by measuring change, following gradients, and step by step minimizing the error. Training a model is really just optimization over a landscape. And third, probability. This is how uncertainty is modeled and interpreted. Because real world data is noisy, incomplete, and never perfectly predictable. Probability tells us how confident a model is, not just what it predicts. Together, these three pillars turns data into decisions and mathematics into intelligence. But these pillars don't stand independently. They build on each other and everything begins with representation. Before we can optimize our reason probabilistically, we must decide what even is our data. Consider the famous iris dataset. Each flower sample is described by four measurements: sepal length, sepal width, petal length, and petal width. Instead of thinking of these as separate numbers, we group them into a single object. This is not just a convenient storage, this is a conceptual upgrade. We have moved from numbers to vectors. So, what a vector really is? A vector is not just a list of numbers. A vector is an element of mathematical structure where addition and scaling makes sense. We can add vectors, scale vectors, compare directions, and measure distances. This structure is called a vector space. Formally, a vector space is defined by operations and rules, not pictures. It contains a set of vectors, a field of scalars, addition, scalar multiplication, axioms that guarantee consistency. R just means real numbers. So Rn is the space where each data point is a vector made up of n real values. This is why machine learning lives in Rn, because almost all features we work with are real valued. Example: R1 is a line, R2 is a plane, and R3 is a space where we live in. But machine learning doesn't stop at three dimensions. If your dataset has 10 features, you are in R10 dimension. And if your datasets have 1000 features, then you live in R1000 dimension. You can't see these spaces, but models operate inside them all the time. Every prediction your model makes is just a point moving through high dimensional space. Understanding Rn is how you understand why models overfit, why distance matters, and why feature scaling changes everything. Feature scaling is a geometric necessity. Let's look at the raw iris dataset features. Some features have a large spread and others are tightly packed. Now, here's the key idea most people miss. Machine learning algorithms don't understand meaning, they only understand magnitude. If one feature ranges from 0 to 1000 and another ranges from 0 to 1, the larger one dominates the geometry and the model listens to whoever is loudest. So we understand there are number of features are present in a vector spaces and that has different ranges. So we need to standardize that each feature and we subtract the mean and divide by the standard deviation. Here's the important part. This is not just pre-processing. This is not a data cleaning trick. This is a geometric transformation of a vector space. We are reshaping the space so that distance, directions, and angles actually means something. Only then can gradients flow correctly. Only then can learning be fair. And feature scaling doesn't help the data. It helps the geometry the model lives in. So, if you only see vectors as numbers in arrays, you miss the big picture. Understanding the vector spaces lets you reason about embeddings, understand PCI and representation, analyze neural networks geometrically, detect when intuition falls in high dimensions. This is why serious machine learning starts with linear algebra. In the end, visualization ends at R3, but machine learning begins at Rn. And once you stop trying to imagine vectors and start reasoning about structure, the math suddenly clicks. Thanks for watching. If you found this video helpful, don't forget to like, share, and subscribe. Follow the channel for more informative videos like this. See you in the next one.